to study the characteristics of a common emitter NPN transistor and to find out the values of current and voltage gains. The apparatus used in this experiment are an NPN transistor characteristic apparatus and connecting wires. In the real world, a transistor looks like this, and in the circuit diagram, an NPN transistor is represented this way. In NPN transistor, a p-type semiconductor is sandwiched between two n-type semiconductors. The first thick layer is called the emitter, which is heavily doped. The second thin layer is lightly doped, and the third layer is the collector. Here, the collector section is larger than the emitter section. In emitter-based forward bias, the electrons, which are the majority carriers in n-type emitter region, move into the base region. This current is called emitter current IE. Out of the larger number of electrons, 2% combine with the few holes in the base, causing a small base current IB. The other 98% of the electrons cross over the collector base junction and enter the collector region, and they are attracted by the positive of the power supply VCC. This current is referred to as IC. To study the characteristics, let us connect the NPN transistor in the circuit. For input characteristics for different constant collector voltage, we notice the corresponding change in the base voltage and base current IB. For output characteristics for different constant base current IB, we notice the corresponding changes in the collector current IC and the collector voltage VC.
Now that you have understood the working of an NPN transistor and the procedure for this experiment, let me explain the apparatus. This is the on-off switch for the power supply for this circuit. Since we are going to study the characteristics of an NPN transistor, we will be using this transistor, which is labeled as NPN transistor. These two blue terminals are the emitter of this transistor. These two red terminals represent the base of the transistor, and these two yellow terminals represent the collector of the NPN transistor. This knob is actually a rheostat which can be used to vary the voltage from 0 to 1000 millivolts. This voltage will be applied between the base and emitter of the NPN transistor. Since it is the input voltage, it will be small and is therefore measured in millivolts. Thus, this voltmeter is used to measure the base emitter voltage. This knob here is again a rheostat which can be used to vary the voltage from 0 to 10 volts, and this voltage is applied between the collector and emitter of the NPN transistor. Since it measures the output voltage, it is comparatively larger and is therefore measured in volts. Thus, this voltmeter is used to measure the collector emitter voltage. This toggle switch can be used to set the range of this ammeter to either 250 microamperes or 25 milliamperes. Since this ammeter will be used to measure the base current, which is supposed to be small and in microamperes, we will set this toggle switch to 250 microamperes. This ammeter will be used to measure the collector current, which is the output current, and is comparatively larger, and so will be measured in milliamperes. Now that you have understood the layout of the apparatus, let's make the connections. We have with us here two connecting wires of 2 pins each, two connecting wires of 3 pins each, and one connecting wire with 5 pins. So we have to make all the connections using just these 5 connecting wires. Let's start with the 5-pin connecting wire. As you can see in the circuit diagram for the common emitter configuration of an NPN transistor, the negative terminals of the two power supplies, the negative terminals of the two voltmeters, and the emitter are all connected together. So let's connect these 5 points using this 5-pin connecting wire. Now let's use these 3-pin connecting wires. As you can see in the circuit diagram, the positive terminal of the power supply, the positive terminal of the voltmeter and the positive terminal of the ammeter are all connected together in both the input and output circuits. So let's connect the positive terminal of the voltmeter, ammeter and power supply in the input circuit using this 3-pin connecting wire. Similarly, let's connect the positive terminal of the power supply, voltmeter and ammeter in the output circuit using this 3-pin connecting wire. Now let's use these 2-pin connecting wires. As you can see in the circuit diagram, the negative terminal of the input ammeter is connected to the base of the transistor since it has to measure the base current, and the negative terminal of the output ammeter is connected to the collector of the transistor since it has to measure the collector current. So let me connect the negative terminal of the input ammeter to the base of the transistor using this connecting wire. And let me connect the negative terminal of the output ammeter to the collector of the transistor using this connecting wire. The connections are now complete. So let's start the experiment. Use a screwdriver to remove the zero errors, if any, in the ammeters and voltmeters. As you can see, there is no zero error in the ammeters and voltmeters here. So let's note down the least count and range of the ammeters and voltmeters. The range of the input voltmeter is 0 to 1000 millivolts and its least count is 200 millivolt divided by 10 divisions, which is 20 millivolts. The range of this ammeter here is 250 microamperes, since right now the toggle switch is set at 250 microamperes. The least count in this setting is 50 microamperes divided by 10 divisions, which is 5 microamperes. If I set the toggle switch to 25 milliamperes, the range of this ammeter will be 0 to 25 milliamperes and its least count then would be 5 milliampere divided by 10 divisions, which is 0.5 milliamperes. Since this ammeter will be used to measure the base current, which will be in microamperes, this toggle switch is set at 250 microamperes, and so the range will be 250 microamperes and least count will be 50 divided by 10 divisions, which is 5 microamperes. The range of this ammeter is 25 milliamperes and its least count is 5 milliamperes divided by 10 divisions, which is 0.5 milliamperes. The range of this voltmeter is 10 volts and its least count is 2 volts divided by 10 divisions, which is 0.2 volts. We will first take the measurements to study the input characteristics of the NPN transistor in common emitter mode. A graph between the base emitter voltage VBE on the x-axis and the base current IB on the y-axis for a constant collector emitter voltage VCE is called as the input characteristic of the transistor in common emitter mode. To plot this graph, we need the values of base current, for different values of base emitter voltages for a particular value of collector emitter voltage. So we will first set the collector emitter voltage to 0 volts. Let's switch on the power supply and let's set the base emitter voltage and collector emitter voltage to 0. While keeping the value of the collector emitter voltage constant, we will now note down the value of base current for different values of base emitter voltage. So, for base emitter voltage of 0 millivolts, the base current is 0 microamperes. For base emitter voltage of 100 millivolts, the base current is again 0 microamperes. Like this, increase the base emitter voltage in steps of 100 millivolts and note down the corresponding value of base current till you cover the entire range of the input voltmeter. So when the base emitter voltage is 200 millivolts, again the base current is 0 microamperes. When I increase it to 300 millivolts, again the base current is 0 microamperes. When I increase it to 400 millivolts, again the base current is 0 microamperes. When I increase it to 500 millivolts, the base current has increased to 15 microamperes. When I increase it to 600 millivolts, I now find that the base current has increased drastically to 95 microamperes. So since we are finding a sudden increase in base current, let's take the measurements for base emitter voltage in smaller intervals. So let's go back to 500 millivolt and now increase the base emitter voltage in steps of 20 millivolts. So for 520 millivolts, the base current is 20 microamperes. For 540 millivolts, the base current is 30 microamperes. For 580 millivolts, the base current is 75 microamperes. Like this, let's take for 640 millivolts, we find that the base current is 175 microamperes. And we see that if we increase the base emitter voltage further, the base current goes out of scale. So we have got sufficient readings to plot a good graph. Next, increase the collector emitter voltage to 2 volts and repeat the same steps to note down the base currents for the same set of base emitter voltages. Repeat this procedure for collector emitter voltage of 4 volts, 6 volts and 8 volts. And record your observations in the observation table.
Here, the least count of the input voltmeter VB is 20 millivolts and the least count of the output voltmeter VC is 0.2 volts. The least count of the input ammeter which measures the base current is 5 microamperes. And finally, the least count of the output ammeter which measures the collector current is 0.5 milliamperes. For a base voltage VB 0 millivolts and collector voltage VC 0 volts, base current IB is equal to 0. Now, keeping the collector voltage constant, we increase the base voltage and note down the readings of base current IB. Similarly, for constant collector voltage Vc of 2 volts, 4 volts, 6 volts and 8 volts, the values of base current Ib are as follows. Calculation of input resistance. To calculate the input resistance, we plot a graph between base voltage Vb on x-axis and base current Ib on y-axis, and the scale on x-axis is 1 cm is equal to 100 millivolts. On y-axis, 1 cm is equal to 20 microamperes. Now, we plot the points on the graph. Here, the slope of the graph is given by delta y by delta x is equal to delta Ib by delta Vb, that is 125 divided by 700. Its reciprocal is the input resistance, which is delta Vb by delta Ib is equal to 700 by 125, which is 5.6 ohms. Therefore, input resistance Ri is 5.6 ohms.
Now, let's take the measurements to study the output characteristics of the NPN transistor in common emitter mode. A graph between the collector emitter voltage VCE on the x-axis and the collector current IC on the y-axis for a constant base current IB is called as the output characteristic of the transistor in common emitter mode. To plot this graph, we need the values of collector current for different values of collector emitter voltages for a particular value of base current. So let's switch on the power supply and set the collector emitter voltage to 0 volts and adjust the base emitter voltage such that the base current is 25 microamperes. While keeping the value of the base current constant, we will now note down the value of collector current for different values of collector emitter voltages. So, for collector emitter voltage of 0 volts, the collector current is 0 milliamperes. Now, when I increase the collector emitter voltage to 1 volt, I find that the base current has suddenly decreased. So I need to readjust the base current to 25 microamperes before noting down the collector current. So now, for a collector emitter voltage of 1 volt and base current of 25 microamperes, the collector current is 4 milliamperes. So next, I will increase the collector emitter voltage to 2 volts. And again I check whether the base current is 25 microamperes. It is 25 microamperes. So now I can note down the collector current as it's again 4 milliamperes. Like this, increase the collector emitter voltage in steps of 1 volt and note down the corresponding value of collector current till you cover the entire range of the output voltmeter. So when the collector emitter voltage is 3 volts, the collector current is again 4 milliamperes. When the collector emitter voltage is 4 volts, the collector current is again 4 milliamperes. It's the same for collector emitter voltage of 5 volts, 6 volts, 7 volts, 8 volts and even 9 volts. Thus, when increase the collector emitter voltage, the collector current remained constant. Next, increase the base current to 50 microamperes by adjusting the base emitter voltage and repeat the same steps to note down the collector currents for the same set of collector emitter voltages. So repeat the procedure for base currents of 75 microamperes, 100 microamperes, 150 microamperes, 200 microamperes and 225 microamperes, and record your observations in the observation table.
Here, the least count of the input voltmeter VB is 20 millivolts and the least count of the output voltmeter VC is 0.2 volts. The least count of the input ammeter, which measures the base current, is 5 microamperes. And finally, the least count of the output ammeter, which measures the collector current, is 0.5 milliamperes. Output characteristics. For output collector voltage VC is equal to 0 and input base current IB is equal to 25 microamps, the output collector current IC is equal to 0 milliamperes. Now, keeping the base current constant, we note down the collector current by increasing the collector voltage. Similarly, for constant base current of 50, 75 and 100 microamperes respectively, the values of collector current IC are as follows. Calculation of output resistance. To calculate the output resistance, we plot a graph between collector voltage VC and collector current IC using the values from the observation table. Consider the collector voltage on x-axis and collector current on y-axis, and the scale on x-axis is 1 cm is equal to 1 volt and on y-axis 1 cm is equal to 5 milliamperes. Now, we plot the points on the graph. Here, the slope of the graph is given by delta y by delta x is equal to delta IC by delta VC. Which is 4 divided by 1. Its reciprocal is the output resistance, which is delta VC by delta IC, that is equal to 1 by 4. Therefore, the output resistance RO is 0.25 ohms. Calculation of current gain. To calculate the current gain, we plot a graph between the base current IB and the corresponding collector current IC using the values from the observation table. And on the scale on the x-axis is 1 centimeter is equal to 10 microamperes, and on y-axis 1 centimeter is equal to 2.5 microamperes. Now we plot the points on the graph. Here, the slope of the graph is given by delta y by delta x is equal to delta IC by delta IB. Which is 17 divided by 75. It is nothing but the current gain beta, that is equal to 17 by 75, that is equal to 0.2266. Calculation of voltage gain. Voltage gain is equal to current gain into resistance gain, where resistance gain is equal to output resistance divided by input resistance, that is equal to beta into RO by RI, which is 0.2266 into 0.25 divided by 5.6. Therefore, the voltage gain is 0.0101. All the connections should be neat, clean and tight. Key should be closed only when we are taking the readings. Forward bias voltage beyond the breakdown should not be applied. Reverse bias voltage beyond the breakdown should not be applied. Make sure that the input and output voltages are zero biasing before switching on the circuit. You should note down the readings without any parallax.